We are presenting Hyperblock floating point, which is a generalized quantization scheme that can be used both during inference and during training of convolutional neural networks. The majority of quantization literature has focused on inference only. However, each iteration of the backpropagation algorithm during training can take 2 times the energy and time when compared to the forward pass. The problem of quantizing the backward pass is that gradients are very hard to quantize due to a mix of the need for higher granularity and the problem of stagnation, which occurs when the gradients are always quantized down to 0. The solution proposed in this paper is to use a combination of block floating point to solve the granularity issue and stochastic rounding, which solves the stagnation problem. Block floating point is a number format that lies in between fixed point integer numbers and floating point numbers. Fixed point numbers are very energy efficient when performing operations but lack scale, whereas floating point numbers are expensive to compute but can provide larger scale. Block floating point is a format that balances both. The idea is that instead of having one exponent for each number, like in floating point format, we share an exponent across a block of integer values. This allows us to perform the great majority of operations in fixed point while still retaining some of the scaling power of floating point numbers. Block floating point is applied across channels. This allows us to calculate dot products in convolutions using integer operations. The problem with using formats during the training is that the backpropagation algorithm, the tensors in the convolutions are transposed, which means that channels are now batches and vice versa. As can be seen in the image, this means that the same exponents that were shared across the same dimension now are in different batches. Therefore, integer multiplications can no longer be carried out. We propose a solution to this problem by using hyperblocks. The idea is that instead of sharing an exponent across channels only, we can share exponents across both dimensions, channels and batches. Once we share across both dimensions, they become invariant to transposition. As it can be seen in the picture, during the forward pass using BFPs, the numbers in the channels are aligned, but as soon as the tensor is transposed, this is no longer valid. Every pair of numbers have different exponents. By using hyperblock floating point format, once the numbers are transposed, they are still sharing the same exponent. Therefore, both inference and backpropagation can be performed without changing the quantization scheme. By using hyperblock, it also means that we can save the number of quantization passes our tensors need to perform. The left-hand side shows a naive way of implementing quantized backpropagation. Since block floating point is not invariant to transposition, we need to keep the original tensors in memory and quantize them both during the forward and backward pass. This means that a total of 6 quantization passes will be performed. When using hyperblock, though, we can reduce it to 3 quantization passes only, as shown in the figure on the right. That's because the same tensors that were quantized can be transposed and reused in the backward pass. The last trick to make this all work is to quantize the gradients by using stochastic rounding instead of normal rounding. Differently than round, floor, or seal operations, stochastic rounding yields random results. For example, by using stochastic rounding, 0.8 will have an 80% probability of being rounded to 1 and 20% probability of being rounded to 0. This means that no matter how small a number is, it will always have a chance to be rounded up instead of being rounded down. This helps tremendously in training because it avoids gradients to be rounded down to 0. The graph on the right shows this. The lines indicated by P0, 0.2, etc. show the percentage of values that are rounded stochastically. As it can be seen, the higher the percentage of values being stochastically rounded, the higher is the top one accuracy achieved. After implementing Hyperblock and stochastic rounding, we benchmarked them using both SVHN and ImageNet results. As can be seen, we were able to train ResNet 18 network using only 5 bits with less than 1% degradation in accuracy.